Now that we have seen the challenges behind scheduling when we have multiprocessor architectures, hardware, let's look at some scheduling strategies for this kind of architectures. And let's start with time sharing. So something we can do is to share one multiprocessor architecture under the time domain. So basically all processes can run, but they need to share over time the resource. We can go for something simple here. We can have a single system-wide data structure. In this case, we can have priorities, and then within each priority level, we could iterate using round robin. And we keep here all the ready threads, and whenever CPU goes idle, we take the next ready process we have in the queue with the highest priority. So when this CPU 4 goes idle, we put process A, which was here the first with the highest priority. Then CPU 12 goes idle, we take B, which was here the current next ready process with the highest priority, and so on and so forth. It achieves, it balances the load automatically, because after a while all threads will be used and all cores will be used, and all threads can be assigned to any core. There can be, of course, contention, because you have a single data structure where you keep everything, but you suffer from the affinity problem, the one I mentioned before, about the fact that cores have their own caches, and if you schedule a thread in the same core it was running before, then there are higher chances that the thread will find some stuff in the cache that is already valid, and it will require less interaction with the main memory, so it will perform better. What you can do is to have a two-level scheduling algorithm when you go for a time sharing option, okay? So you could have these data structures, or let's say the collection of threads you have. You can have one for each CPU, and you assign these threads to the CPUs at creation time. Of course, it doesn't need to be strict, meaning that if a CPU has nothing to do, it's still better to steal some threads and do something that, even if these threads are assigned to other CPUs, that just let the CPU go wasted, okay? But you still have, you can still achieve a balanced load, but then you have also cache affinity, because you, with high probability, place each thread back to the core it was running before, and also less contention, because you have this dedicated per CPU lists or sets of threads. Something different you can do is then, instead of time sharing, to go for space sharing. So when a set of related threads, okay, so a process that is multi-threaded is created, the operating system, assuming there are, of course, enough cores, enough CPUs, it will try to schedule all the threads at the same time, okay? And then it lets the threads run until they are done, okay? Here we don't care about the time dimension. So if one specific thread that belongs to a group of threads is actually requesting some input-output, we don't release the CPU core to give it to another thread. We just wait for the input-output to be done, and then we keep running all the threads all the threads that belong to the same process as a single block, and they are placed into the same CPU, so close by. This can also be beneficial, as we said before, for non-uniform memory architectures. Then what you can do is, in practice, to go for a mixture of the two. So you share both on time and in space, and this is what gang scheduling is. So you see that the problem with space sharing is that it can be inefficient, because if you have a lot of IO bound processes, why would you waste cores giving them to threads that are just waiting, instead of reallocating them to something else? But on the other hand, if you go for time sharing, you can have situations like the following one here. Suppose you have A0 and the A1, they are two threads, they belong to the same process, and one is a producer and one is a consumer, so they need to communicate. you can end up scheduling the threads like this. So it's A0 that runs, then A1, A0, A1, and so on. Here you could potentially waste a lot of time because A0, it starts running, but sends a message to A1, and until A1 does not reply, A0 cannot move forward. So this entire quantum can go basically wasted because A0 is waiting for a reply from A1. Then you start running A1 here. It sends the reply back to A0, and then it has nothing to do until A0 sends a new request. And this quantum is also wasted. And you can see that you can end up in these kind of situations if you just try to schedule on time. Okay, so what you do is that you try to schedule groups of related threads at the same time, but also close by. So trying to take into account both time and space. Okay, all gang members run at once, and all gang members start and their quantum together. This is just an example of a possible execution. So you have 6 CPUs here, and these are the time slots. So you see that for a certain slot, you run process A that has 6 threads. At the slot 2, you run on the first 3 CPUs B, and on the last 3 C. Then you run D here and E, and you keep running E on all the CPUs also in the next slot, and so on. So you can see that there is time sharing, but then there is also groups of threads that belong to the same process that are run at the same time to maximize also space sharing.